Okay, I think we're live. Apologies for the minor delay. It's always this thing with trying to do a podcast. I am very very excited to have the one and only Professor Scott Aaronson from University of Texas at Austin, the leading expert on quantum computation, probably in the
Well,
world.
well, I
Oh,
don't know about that.
okay. Well, okay. I don't know either, but that's what I'm going to say, and it's a belief I hold. So, we're going to talk a lot about what exactly is going on with quantum computation, especially with its effect and potential impact on Bitcoin, and by extension, other cryptocurrencies. How much of a threat is it? What is being done? How imminent is it? And what can be done to prevent whatever catastrophe lies out there. At the same time, quantum computation is this, beautiful, magnificent, and mysterious to most of us mortals topic. I'll share a little bit about myself, but first of all, Professor Aronson, I'm going to call you Scott, if that's fine. How the hell did you get
Of course,
into?
it's fine. I mean, you and I go back decades, right? And it's very good to see you, Ellie.
Thank you. It's so good to see you. So, Scott, how the hell did you get into quantum computation?
Well, I mean, I was obsessed with programming as a teenager, and I learned this from there about algorithms. From there about the P versus NP problem, things like that. And this was in I would say the mid to late 1990s. And at some point, I encountered a popular article about this guy named Peter Shor, who had just supposedly discovered a method for factoring numbers. The way the article described it, it wasn't entirely clear, but it was something about trying all the possible divisors in different parallel universes or something like that. And my immediate reaction on reading this was, even though, I was, again, only a kid at the time, was, this sounds like garbage. This sounds like the physicists just do not understand what they're up against. They think that they can just rewrite all the rules of computer science, right? There's going to be some reason why this is not going to work or scale. It just sounded too good to be true. But I had to learn something about it, and there were already at that point web pages explaining Shor's algorithm, Grover's algorithm, another important quantum algorithm that had recently been discovered. And and then I realized, okay, we have to back up. First thing I need to understand is, what is this quantum mechanics? What does it say about the world? And to me, maybe the biggest surprise was that despite not knowing so much physics, I could actually understand it, because really, these explanations I was reading were not talking about physics. They were talking about linear algebra. They were talking about matrices and vectors and complex numbers that you take the squared absolute value of to get probabilities. And I said, I can do that, right? How come no one told me? This is what it is, right? And then and then based on that, you can understand, on the one hand, how this could actually work to factor a number, by the Shor's algorithm. But on the other hand, this is a really, really special thing, taking advantage of really, really special structure in some particular problems. It's not just a simple matter of trying every possible answer in parallel. It's this much more subtle thing to do with interference. But then you say, well, if this is really how the world works, then the default assumption should be that this is possible. The burden of proof shifts to anyone who thinks this is not possible, right?
Mhm.
They have to explain what is new or surprising about physics that would prevent this. And at the time, quantum computing was still very new. There was a lot of low-hanging fruit. I happened to be doing a summer internship at Bell Labs in 1998, I think, that had nothing to do with quantum computing. But my boss was nice enough to let me spend, a month investigating it. I discovered that Lav Grover, the discoverer of Grover's algorithm, worked in the same building. So I sought him out, and I, told him all my ideas for improving Grover's algorithm, which were completely wrong. They just were just complete nonsense. But Grover was extremely kind and invited me to do an internship with him the following summer. And it was really that summer that I met, students from Berkeley, students of Umesh Vazirani, who was then, building maybe the central group in the world for quantum computing theory. And I said, this is what I want to do, right? I want to learn, whatever it is that these people know.
Beautiful.
And I wasn't sure that I could do anything new in it, and I was also very tantalized by this AI thing, which seemed like it might become a big deal at some point. But eventually, quantum computing was just too much fun for me, and so that was 25 years ago, and it's remained fun to this day.
Very inspiring. Thank you for sharing. Before we go on to the next question, and those of you who want to hear, we're going to unpack everything that can be explained in, roughly 60 minutes about the quantum threat and what quantum computers actually do in layman's term. I'll just say briefly, I'm Eli Ben-Sasson. I'm co-founder and CEO at Starkware. I co-founded two crypto projects. The first is Zcash, based on ZK technology that actually is susceptible to quantum attacks because it uses elliptic curve cryptography. The second is Starkware, which uses ZK Starks, which is actually resistant to quantum computers. I used to do math. Now I run a company working on expanding Bitcoin economy. So I care deeply about Bitcoin. I got red pilled into crypto in 2013 because I fell in love with Bitcoin. So I really care about I don't understand much about quantum computation, like probably most of our listeners, but I do care very, very deeply about how to avoid, its damages. And we'll get to that. But before that, just one more, personal question. For those who don't know, Scott is one of the most prolific and eloquent writers on so many different topics. He has this beautiful blog, shtetloptimized.org. I recommend everyone to go and read it.
Or was it ScottAaronson.com?
Oh, sorry, ScottAaronson.com. The blog is called
/blog. Yeah.
Yep. And and in particular, it is the source of most of where I and others get our information about quantum computation. But there are a lot of other very interesting topics there. So I want to ask you, Scott, how do you find time to basically read, learn, and then write so much about so many diverse topics? There are only 24 hours a day.
It's always funny when I get that question, because from my point of view, I just waste so much of my time. I'm either reading the news, getting depressed about all the things happening in the world, reading various people, arguing on Substack, on Facebook, in my blog comment section. But then, sometimes I have something that just I need to get out. And then I just find that I have written something, right? So I don't have any kind of schedule that I keep, any kind of organized plan. But I guess if you just integrate that over 20 years, which is how long I've been blogging for, just every week or so you get annoyed and you write something, then that ends up being a lot of posts.
Okay, thanks. Now, let's get to a topic that is, dear to both of us. We spent a lot of time on it, basically science and math. Okay, you get asked this a lot, but please help our audience. What the hell is a quantum computer for those who don't have a PhD in physics?
Yeah. So, which I don't either. I mean, but a quantum computer is a device that would exploit the laws of quantum mechanics to solve certain specific problems much faster than we know how to solve them with a conventional computer. To explain that a little more, we have to back up and say, what are these laws of quantum mechanics? right? And I like to say that quantum mechanics is actually really surprisingly simple once you take the physics out of it. As I was saying before, what it really is a certain generalization of the rules of probability themselves, right? So in normal probability, you could talk about, a 30% chance or a 60% chance that it will rain. You'd never talk about a negative 30% chance, much less would you talk about an I% chance, right? But in quantum mechanics, the fundamental numbers that the universe somehow keeps track of are called amplitudes. Amplitudes can be positive or negative. In fact, they can even be complex numbers. Okay, so they're very closely related to probabilities. But the fact that they can be negative or complex means that they're not probabilities. Okay, and the rules are, if you want to know the total amplitude for some event to happen, like for example, a particle to hit a certain spot on a screen, you have to add up the amplitudes for all the different ways that could have happened. Okay, so if there were two different paths that the particle could have taken to get there, each path can contribute an amplitude to the total. Okay, and then what do these amplitudes even mean, right? Well, when you make a measurement, there's a rule for converting the amplitudes to probabilities. Okay, that says the probability that you will see something happen, like for example, that you'll see the photon land at this particular spot, is equal to the square of the absolute value of the amplitude for that to happen. Okay, so what does this mean? It means if you have an event that could happen in two different ways, and one of those ways has a positive amplitude and the other has a negative amplitude, then you can get two contributions that cancel each other out. So now the total amplitude is zero, which means that the probability is zero, which means that thing never happens. Okay, so because the two ways that it could have happened have canceled each other, right? But now, the real test of this is if you blocked one of the paths that the particle could take to reach this place, then now you only get a positive contribution or only a negative contribution, right? Which means that now, I square that, I get a positive number, right? And now I get something that can happen. Okay, so to say that again, I can decrease the number of paths that a particle can take to get someplace and thereby increase the chance that it gets there. Okay, that's the sort of famous signature that we are dealing with amplitudes and not, and what it shows us is that this is not just some little, fiddly detail of how particles behave, right? This is a change to the rules of probability themselves. Okay, this is a change, to something that a priori you wouldn't have even thought was part of the subject matter of physics at all, right? You would have thought, we can, the rules of probability are just sort of a priori, maybe even obvious. We just sit in our armchairs and we think, right? But no, 100 years ago we learned, nature prefers this completely different way of calculating probability. Okay, so now,
maybe, yeah. So I'm trying to rephrase in words of the laws of quantum mechanics allow particles to be potentially or with something like probability in several different situations.
Yeah.
And in particular, maybe I'm already jumping ahead, there's a way to configure the world that all the different configurations, for instance, could refer to all potential different potential divisors of a certain number if we're trying to factor that number. And then magically using some other laws of physics, and then laws of math, we can make sure that all of the non-true divisors, like the fake divisors, will somehow cancel each other out. And the only remaining thing which will actually be amplified will be, the set of particles or their configurations that happens to match to a true divisor of the prime we're looking at.
Well, okay, so that's not quite how it works. It's not Shor's algorithm doesn't work by making a superposition over all the divisors, but it does involve this sort of cancellation. This sort of destructive interference that I was talking about before. Okay, so just to back up a little, when you hear the word superposition a lot, right? What does that mean? It just means your system is you have a physical object that has been isolated from its environment, and now the only true way of describing it is to give a list of amplitudes. Okay, to give the amplitude for each place that it could possibly be. Right. So the basic building block of a quantum computer is what we call a qubit, or a quantum bit. Okay, this is simply a bit that has an amplitude for being 0 and an amplitude for being 1. Right. So it can be in a superposition of the 0 state and the 1 state. Right. And now people always want to ask, what does that mean? Does it mean that it's both of them simultaneously? Does it mean that it is one or the other, in some weird way? We just don't know which one, right? And the point is, this is not a concept that maps neatly onto, any previous concept, right? If it did, it wouldn't be as interesting, right? Yep. This is, it's a complex linear combination of the 0 state and the 1 state.
But when that's you look, God decided to make or whoever decided to make the world.
Yes, no, exactly. God really liked the complex numbers, right? Is one thing that I think we can say, right? But now, if you measure a qubit, then you're going to force it to decide what it wants to be, right? It will pick one option or the other, according to that rule I said before, which is called the Born rule. Right, where that probability equals squared absolute value of amplitude. Okay, and then whichever choice it makes, 0 or 1, it sticks with that choice. Okay, so if you measure the qubit, it tells you it's 0. Okay, now it is 0. Right, you look again, nothing having happened, it's still 0. Okay, but if you leave the qubit isolated, right, then it evolves in a different way. These amplitudes are just undergoing some sort of linear differential equation, okay, which is called the Schrodinger equation, one of the most famous equations in physics, okay, which basically just says, this list of amplitudes, a vector of amplitudes, right, gets updated via some sort of linear transformation, okay, and it's a linear transformation that preserves the norm, meaning, we always have to preserve that the probabilities of the various outcomes will add up to 1. Okay, and one thing that these linear transformations can do is that they can produce interference between different possibilities. Okay, so that this is already we already see all of this with just one qubit, right? And this is already extremely interesting, but it gets even more interesting when we have a lot of qubits. Right. So if we have 2 qubits, let's say, then the rules are unequivocal. Since Schrodinger wrote them down 100 years ago. Okay, that now we need 4 amplitudes. Okay, we need an amplitude for both qubits to be 0. We need an amplitude for the first qubit to be 0 and the second to be 1. For we need an amplitude for 1 0, and we need an amplitude for 1 1. Okay, and so the result of that is I could have a superposition, for example, where either both qubits are 0 or else they are both 1. Okay, but they're never 1 0 or 0 1, right? And so in this situation, we would say that the qubits are entangled. Okay, if I measure one qubit and I find that it's 0, then immediately I know that the other one will also be 0, no matter how far away it is. Right. This was the famous, spooky action at a distance that Einstein never liked. Right. But I hasten to say it doesn't let you actually send a message faster than the speed of light. But it does let you produce correlations that you.
Scott, I apologize for interrupting, but sure. I want to cover a lot of ground. And how does this bring us quickly to understanding?
All right. Well, look, I'm compressing it as far as I can, and I've been trying to compress this stuff for 20 years, but so now what is a quantum computer, right? Well, if I have 3 qubits, now I need 8 amplitudes. right? That's for 2 to the 3rd power, right? If I have 1,000 qubits, now I need 2 to the 1,000 power amplitudes. Okay, that is more than I could write down explicitly using all the atoms in the whole visible universe. Okay, and somehow physics is telling us that just to maintain the state of, let's say, 1,000 particles that are interacting with each other, nature in some place that we don't see has some scratch paper with 2 to the 1,000 parameters on it, right? And every time something happens to these particles, nature has to cross off those 2 to the 1,000 parameters and replace them with new ones. Now, that is a staggering amount of work for nature to be going to, right? And the chemists and physicists knew this for a while. They knew it mostly as just a practical problem, right? If you're trying to simulate some complicated molecule or material with lots of interacting electrons, right, then the wave function, which means the list of amplitudes, right, grows exponentially with the number of particles. And so for decades, they invented all sorts of hacks and heuristics for getting around that problem, and sometimes simulating quantum systems on a classical computer. It was not until the early 1980s that a few physicists, most famously Richard Feynman and David Deutsch, started saying, well, if nature is handing us this computational lemon, then why don't we make lemonade out of it, right? Why don't we build a computer that itself would be made out of qubits, that at least would help us for simulating quantum mechanics itself? Okay, so that's what they called a quantum computer. And but for a decade or so, it was kind of an interesting idea. No one really knew what else to do with it, right? And in particular, no one really knew if this would help in solving any classical problems faster than a classical computer could solve them. Okay, because now I can get to sort of the central point about quantum algorithms. Here's kind of the main difficulty. Okay, it is true, as you were saying, Ellie, that you can make a superposition over all the possible solutions to your problem, even if there are exponentially many of them, right? Like all the possible keys for a cryptographic code, all the possible routes that a traveling salesman would take, something like that's even an easy thing to do. Okay, the trouble is, for a computer to be useful, at some point you have to look at it. You have to measure, get an output. Okay, and if you just measure an equal superposition, not having done anything else, then the rules of quantum mechanics are unequivocal that all you're going to see is a random answer. And well, if you just wanted a random answer, you could have saved the billions of dollars to build this quantum computer. You could have just flipped a coin a bunch of times, right? And so, for this reason, the only hope of getting any advantage from a quantum computer is to exploit the way that these amplitudes, being complex numbers, work differently from normal probabilities. Okay, so with every algorithm for a quantum computer, including Shor's famous factoring algorithm, which he discovered in 1994, right? The basic idea is you're trying to choreograph a pattern of interference so that for each wrong answer, each one that you don't want, some contributions to its amplitude are positive and others are negative. So they're canceling each other out. Whereas for the right answer, you want all the different contributions to its amplitude to be pointing the same way. Okay, and then when you measure, you're going to see the right answer with a large probability. The tricky part is, you have to somehow arrange that, even though you yourself don't know in advance which answer is the correct one. Because if you did, what would be the point, right? And then, you always have to compare, to what is the cleverest classical algorithm that could solve the same problem, do the same task. Am I actually winning compared to it? Okay, so this is nature is giving us this really, really bizarre hammer, right? That we have to figure out what nails it can hit, right? I think it's something weirder than any science fiction writer would have had the imagination to invent. And in some sense, we either got very lucky or very unlucky, right? That we decided to base so much of the world's cybersecurity infrastructure, or public key infrastructure on cryptographic codes like RSA, Diffie-Hellman, elliptic curve cryptography that just so happen to have these mathematical properties that a quantum computer is able to exploit. Okay, to explain that would take us a little more time. We could either go there or in a different direction.
No, okay. So let me try to
Yeah.
summarize that.
Yeah, sure.
That the laws of physics, and in particular quantum mechanics, and the brilliance of some mathematicians exploiting them over the decades, culminated in this beautiful algorithm of Peter Shor that basically says we can use, if we have the right physical device, we can feed it certain problems like factoring integers, which factoring integers and all kinds of discrete logarithm problems, which are the basis, right? The hardness of solving these problems is the basis of many of the most popular things we use to sign transactions on Bitcoin and other blockchains, but also to do things like handshaking and setting up keys for our SSH transactions when we shop on Amazon and stuff like that. And you could feed one of these cryptographic inputs into that physical device if it ever existed, and out would come basically the key that is used to encrypt or sign or own your Bitcoin and stuff like that. And hence, if there were a physical device that could implement Shor's algorithm at scale, its efficient scale, then and fast enough, then all of these different cryptographic schemes would be insecure, because basically they would be breakable. Now,
I should hasten to point out, it's not that quantum computers would break every cryptographic code. Right. So, for example, most of symmetric key cryptography, right, where we agree in advance on the key, is only modestly affected by a quantum computer. A quantum computer,
AES and things like SHA-2.
That's right. Exactly. We should. Right. So, as I mentioned before, there's another very important quantum algorithm called Grover's algorithm. Okay, and that one can solve sort of pretty much any search problem in the square root of the number of steps that a classical computer would take. Okay, so like instead of like if you had a 256-bit key, it would be as if the key length were reduced to 128 bits.
Yes.
Right. So so that will affect things eventually, but you can deal with it by most simply by doubling your key size. Right.
Yes.
So and even for public key encryption, there are these other cryptographic codes that we don't, after 30 years of research on the problem, we still don't know how to break via anything like Shor's algorithm. Okay, most famously, there are crypto systems based on lattice problems, right, or something called LWE, right? And so we do have potential solutions in place, right? But a lot of people get super confused about this. There's how could a quantum computer speed up some things and not other things, right? So I do want to emphasize this point. It is not just about trying every possible key in superposition, right? That's not how it works, right? It's you have to exploit very, very special structure in the case of factoring, Diffie-Hellman, elliptic curve cryptography. It's sort of structure that comes from abelian groups that lets you set up the right kind of interference pattern that concentrates the amplitude on the answer that you want.
So I want to pause here first of all. Welcome everyone who joined a bit late. I am here talking to a very old-time colleague of mine, Professor Scott Aaronson of U Texas at Austin, who I'm saying is the world's leading expert on the quantum computation and its applications to us, and what can we do about it. I'm Eli Ben-Sasson, co-founder and CEO at Starknet, previously a co-founder of Zcash, co-invented a bunch of ZK that is breakable by quantum computers because it uses elliptic curve cryptography, but also of ZK Starks, which are actually immune to them. What we've discussed so far is Scott very beautifully explained, the law is some of the laws of quantum mechanics, and we reached the conclusion that if a large-scale quantum computer existed at some point, this physical machine, then a large family of cryptographic primitives, including ones that are used to sign Bitcoin transactions and transactions on many other blockchains like Ethereum and others, and including on Starknet, and also a lot of stuff that we use when we do handshaking, when we shop on Amazon, would need to be replaced. So now, because, well, basically a quantum computer could break and find the keys used to spending, your 24 words that you're using would be basically discoverable by a quantum computer if it had access to the public key itself. Now I want to ask you, Scott, so the reason I actually reached out and wanted to do this, I think a large impetus to the whole crypto ecosystem, going up in flames about is the quantum flood coming to drown us all, is actually something you wrote on one of your very influential blogs, which is that, I'm not quoting exactly, but like you won't be surprised if before the next US elections, assuming they take place on time, there will already be a quantum computer that is capable of factoring some serious, putting like some serious damage to existing.
I think I said that it's a live possibility, right?
Live possibility.
Yeah, which is different from saying that it's probable. But I think that.
Please explain that. Yeah. What caused it, and why are you saying this now? Because just for those who don't know, Scott is a bit more of the skeptical, or at least not the, you're a very rational and level-headed voice here.
Yeah.
What caused you to change your mind?
First of all, I don't think that I changed my mind in any very dramatic way, right? I have always been an optimist that quantum computers are possible, scalable quantum computers. The sort of default belief, the conservative belief should be that they are possible, right? That they will work, just like the theory said. Very, very hard to predict, exactly how many years.
I actually remember you once saying that either they exist, and it's just an engineering problem, or else there's going to be some beautiful new laws of physics that have to be discovered that show why they cannot exist.
I think that's right. I think that's exactly right. Now, many things we know are possible in principle, like a human space flight to Mars or fusion energy, right? But it can be extremely hard to predict how many years it will take. But of course, sometimes we get surprised, right? In 1938. It looked like a nuclear weapon, it was decades away to most of the physicists in the world, and then something happened that, enormously sped up the timeline, right? So, yeah, right. So, right now, what I would say, I've always, been sort of an optimist that, yes, I will live to see this get built. Or maybe for a cryptocurrency person that would be called a pessimist, right? But whatever it is.
Why 2 years? Like, why are you now?
Yeah. But right. Okay. So I mean, first of all, if every year I said, I think this is 10 years away, then after some point you should start complaining that why have I not updated that, right?
You could say at least years away, and then you
right. But I mean years pass, and I think a lot of the key engineering milestones are now behind us. Okay, they've now been demonstrated, many of them just within the past year, right? And so so. Well, I mean, in 2019, Google's group, demonstrated this, experiment with 53 entangled qubits, right? That at least by any method that they knew was very hard to simulate with a classical computer, right? This was what had become known as quantum supremacy. Okay, and I had been very involved in sort of laying the theoretical foundation for this type of experiment, which so I could say. We did not design it to be useful for anything. Okay, we just designed it to be something that would be hard for a classical computer to simulate. Okay, now Google's initial experiment in 2019 was not nearly as hard for a classical computer as they had hoped it would be. Right, if you use a large computer, you use some clever algorithms, which are called tensor network contraction. You can simulate. It turned out that you could simulate it pretty easily. But as the Google folks predicted at the time, the quantum hardware was also going to rapidly improve, right? And now these days we can do that kind of experiment with 100 or so qubits, and using the best classical algorithms that we know, even running on a large supercomputer, the estimate is that you would need something like 10 to the 25 years to simulate this, right? So this is
not refer to stuff that happened in the last year. That's it. Yeah. So the jump from like 53 bits.
Okay, well, I mean that's one of the things that's happened. But I a lot of times people fixate on just the number of qubits, right? And the trouble with that is that there are companies, maybe I shouldn't name names, that will sell you devices with thousands of qubits, but the qubits are just not very good, right? What do I mean by not very good? I mean they don't maintain their quantum state for a long time. Right? They don't maintain, the superposition of the 0 state and the 1 state, what we call quantum coherence, for a long enough time, or they don't let you do operations, gates on the qubits with sufficient accuracy. So the most important number that I look at is would be like the fidelity of a 2-qubit gate. Okay, so how accurately can I do one of the basic quantum logic gates that would just cause 2 qubits to interact with each other, and form an entangled state, right? And because there was a beautiful theory developed in the 1990s called the theory of quantum error correction and quantum fault tolerance, and we could talk about it for a long time, but the basic upshot of the theory is that as long as you can do 2-qubit gates with sufficient accuracy, doesn't have to be 100%, okay, but does have to be at least, let's say, 99.9% or something like that. Okay, then there are these very clever quantum error correcting codes that let you simulate effectively perfect qubits, right? So and this came as a surprise to people, right? This was not obvious that error correction would work this way. Okay, but it does. So this was a major theoretical development in the 90s that sort of convinced most of the field that yes, building a scalable quantum computer should merely be a staggeringly hard engineering problem, right? It should not require anything impossible. Okay, and since then, I think maybe if I had to pick one way to measure the progress of the field, it would be by like how accurately could people do a 2-qubit gate. When I entered the field, in like the late 90s, it would be a huge advance to just do a 2-qubit gate with 50% accuracy. Okay, so then you just can't chain together any number of them, right? It all looks very unimpressive. Okay, but then at some point that 50% became 90%. The 90% became 95, 99%, right? With Google's experiment in 2019, they had about 99.5% accurate 2-qubit gates. Okay, and within the last year or two, the new state of the art is like 99.9%, right?
So okay, so let me see if I got it. So you're saying both the number of qubits has, let's say, doubled over the past 5 years, including things that you learned in the past year or two, and the fidelity of which is another very important parameter has increased dramatically.
Yeah. Well, I would say
you're saying now you're like more optimistic about these things.
So look, with each engineering milestone, right, as long as it's sort of there hanging over people's heads, no one can achieve it, it's sort of in the back of your mind, like, gosh, what if the skeptics are right? What if this really is a bottleneck that will take decades to reach, right? So then each time one of these milestones is achieved, then you're like, oh, I guess it does work. It does all work, just like the theory said in the 90s, right? And so then you just sort of continuously update, based on that, right? And we've seen a bunch of milestones cleared within the last couple of years. This past year, I would say, there's a few companies in particular, Google, Quantinuum, which is the startup in Colorado that does trapped ion qubits,
Scott, I want to leave a few more minutes to discussing also the implications to Bitcoin, and also some calming words about what can be done and what is being done by many folks in the Bitcoin community. But before that, I just want to ask you, what would be the one thing to look out for where, for instance, if you saw it, you would basically write in your blog, all hands on deck, drop everything. The quantum computer is like right around the corner. What is this one thing that you're saying, if you hear that, like, okay, game over?
Well, I think that it's pretty much just a continuous progression at this point, right? So, I mean, I can tell you exactly what the next, milestones are along this path.
What a 10x reduction in the error.
Yeah. So now, because of the accuracy with which people can now do 2-qubit gates, they can now, a huge milestone that Google demonstrated a year ago was to demonstrate a single error-corrected qubit, okay, that actually improves as you use more and more physical qubits to encode a logical qubit, right? The logical qubit stays alive for longer and longer, okay? So they pass that threshold. Right now, a next threshold to pass will be showing that you can do a 2-qubit gate between two error-corrected qubits, right? And do it more accurately than you could do a 2-qubit gate on the bare physical qubits, right?
So you're saying like what you making predictions is very hard, especially about quantum states. Even though we understand the laws of quantum mechanics, but you're saying what we can expect, even in an optimistic world of quantum computation, we'll see more of the same, maybe with more and more impressive, like, higher fidelity, which gets converted into more and more of these, logical qubits and stuff being done on them.
I mean, like there is no, I don't see any discrete giant breakthrough that has to happen. I see a lot of engineering that has to happen. Okay. And but now the things that we're going to see along the way, I think that we would surely see, before, Shor's algorithm is threatening RSA, right? Is we're going to see, first of all, networks of multiple error-corrected qubits, that are used, at first to do very small computations. And that might not sound impressive because, haven't we been doing small quantum computations for decades now? But these are going to be computations on error-corrected qubits, right? On the kind of qubits that ought to scale, okay? Where each error-corrected qubit might have to be built out of 100 or more underlying physical qubits. Okay, so that's the next thing to look. And then another thing that we should expect to see, within the next few years, are quantum computers being used to simulate quantum mechanics in interesting ways. Okay, to do simulations of condensed matter physics, for example, of material science. Right, telling the material scientists things that are interesting to them, and that they may have wanted to know that they couldn't have easily gotten with a classical computer, right? I think that should be feasible well before any quantum computation that would threaten cryptography. Okay. But then at some point it just becomes a matter of scaling, right? Once you have these error corrected qubits, and once you're past the error correction threshold, which means like you are correcting errors faster than you're introducing new ones, right?
Yeah, then things are going to move very fast.
You have stabilized your qubits. Then at some point, it's just a matter of engineering, a system at sufficient scale, right? Where, no one has ever done this before. No one has ever built a system with millions of physical qubits that are all getting shuttled around to where they have to be, and you might, initially need like entire buildings that are filled with dilution refrigerators or, filled with equipment for shuttling these qubits around.
Just a little bit like those super collider things.
Just like the early classical computers, filled buildings, right? That may be what it looks like at first, but I don't see, I feel like if there were a showstopper along the way to that, then we probably would have already noticed it.
Okay, I want to say a few words. As an expert on the cryptography of, as a non-expert on quantum mechanics, but and quantum computation, but as an expert on the, let's say, use of cryptography within blockchain. So I want to say there should be a sense of urgency. There actually is a sense of urgency among Bitcoin developers and other ecosystems, but we should not be complacent. So let me now expand on that. Let's take Bitcoin because it's the most important and blockchain out there, the one largest in its value. First of all, I highly recommend reading Nick Carter's sequence of blogs. He only released, to the best of my knowledge, 2 of them. The third is going to come there. For those of you who are not experts on quantum computation but do care about blockchain, I think he does a spectacular job of speaking very level-headed about what exactly is going on. But I want to say a few words. If nothing is done and a quantum computer arrives, then that would be extremely bad for Bitcoin and it's for its value. And I want to say more than that. If nothing is done, and even the type of exciting news that Scott is saying may happen, even that could be very dramatic in its potential effect to the Bitcoin price, because basically a lot of people, when they look at the price of Bitcoin and its value, they are, this is like hard asset money, cryptographically secured. But if the cryptography is soon to melt and not enough is being done, then that will have a very dramatic effect, which is why both in my tweets and, also behind the scenes, I'm speaking to a lot of core developers and teams about, hey, let's get shit done. And, it's not a secret that the speed at which Bitcoin core development is progressing and the kind of stuff that is often seeing heated arguments is just not at the order of magnitude similar to the kind of changes that would need to happen in order to avert this, especially if it's not a decade away, but let's say 2 years away. And again, you don't need the quantum computer to be here for that. Even if we start seeing more and more of the kind of exciting news that Scott just mentioned, and not enough is being done, and people are still arguing about op return and, various things that may be important, but there's an iceberg that might hit us. We're on the Titanic and we better change course. That's a problem. Okay, so if nothing is done, that would be catastrophic. However, now I want to say the calming things. There are a lot of folks, very serious folks, for instance, Hunter Beast, Ethan Haleman, and a bunch of others pushing forwards things like BIP 360. I don't want to mention names, but, folks from a lot of leading core developer and protocol developer teams are putting serious resources into doing the following: offering a soft fork that would allow to replace, those interested to replace the signature. So the soft fork would, introduce some sort of new post-quantum secure signature. And then those who want, assuming the quantum computer has not yet started breaking various keys, to basically send their Bitcoin to be under that thing. It's not so simple because it's not just the soft fork of adding that key. Almost all of the proposals that discuss these post-quantum signature schemes, things like Sphinx and Dilithium and Falcon, and we have a ZK Stark based one which we call Ziggy, which is not part of the NIST standard but has a lot of advantages of its own. All of these things, they come with longer signatures, and the processing time for processing a signature could be significantly larger, which means that, either you will end with very, very long Bitcoin script, or you also may have blocks or mempools, clogging up with these kinds of signatures. So probably this implies either some degradation in, TPS and throughput beyond what is already today, or you would need further changes. And of course, all of the infrastructure around it, things like hard wallets, being able to sign with these things, mobile wallets. There's a huge amount of infrastructure that needs to be done in time for that. So just summing this up, there are proponents, definitely for good post-quantum secure signature schemes out there, including being standardized by NIST and other places. There are serious folks and serious teams working on things like BIPs, like in particular BIP 360, which, if implemented as a soft fork, would allow those who act in time to basically move their Bitcoin under a more a post-quantum secure key. There's a whole huge discussion about what about Satoshi's early coins, what to do with them. Not going to go into there. Yeah, that's
I'm kind of curious about that, to be honest.
Well, okay. Let me just say, like, the problem. The problem is that many of Satoshi's and others early tokens, basically, you already have inside the blocks the public key, which is breakable by a quantum computer. So now, okay, if Satoshi decides that this is enough impetus for him or her or them to do something, they could just do what everyone else is doing and move their tokens to a post-quantum secure thing. The trickier thing is what happens if they don't. And then ultimately, there are a bunch of solutions, but I think a lot of them involve this social consensus. And then there's this really interesting question of who's the right Satoshi, right?
Yeah.
Coming after.
There's even an ethical question. Like, at what point is it stealing, and at what point is it just like finding some gold coins on the bottom of the ocean, right?
It's a little bit like right, an analog of this thing. Can God create a mountain God cannot lift? So Satoshi created this system where he said, not your keys, not your coins. And now if Satoshi himself has not moved his coins to some keys, like is Satoshi himself allowed to create something?
Maybe Satoshi actually intended to just like set up a gigantic reward for whoever first builds a scalable quantum computer.
You know what? I like that. I'm sure there are some Bitcoiners who actually probably. I like that. You're saying this could be a price for having a quantum computer built. So just summarizing, my little speech. If action is taken, probably have I don't know what's going to come out tomorrow, but probably there's enough time to allow people to safely move from the current signature schemes to ones that are post-quantum secure. Starkware is just one small component in this much larger ecosystem of Bitcoin. I'm not going to speak for others, but I can tell you that many of the leaders of core developing protocols have said to me in private that they have folks working on it. I'm sure there'll be, and of course, those following the BIP 360 important initiative in other places, can see and contribute there. But I am, and I think we should all be like still deeply worried, because right now, and this is a known fact, like the things that folks are bitterly arguing over within the world of protocol soft forks is like 2 orders of magnitude more petty and non-consequential, and also much less impactful compared to what would be needed to be done in order to implement this soft fork. So I cannot overstress this. It is a relatively easy technological thing to do, only if there's enough consensus and support for saying, yes, this is important, and it is actually, I'll say this: it is more important than whichever side you're on for the op return drama, or what you think about opcat or op CSV and CSFS. So like, I'm not worried if we manage to get our act together. I am deeply worried if we continue to quibble and quarrel on things that are not as important. So there is a message of urgency here. I guess I would like to basically just, wrap up by asking Scott, what is your prediction for first of all, do you think within the next 50 years you think we'll see large scale quantum computers, or do you think we'll see
if we don't see them within 50 years, then something very strange has happened, I think, right? Because look, I have friends who are wondering whether within a few years we're going to have an AI singularity, and presumably after that point, if the AI wants quantum computers, it will just build them. So,
Oh,
I
you're
mean,
saying about the
and,
AI. I didn't understand. The AI is
that
going to
is
come and build the
right.
quantum.
Right. I mean, AI is now sort of the 800-pound gorilla that is like overshadowing quantum computing and everything else, right? But I mean, I think if we can't even build, scalable quantum computers, within the next 50 years, then something, then like my first guess at that point is like, has civilization just collapsed? Has what has happened to prevent that? Right, especially given the progress of the last few years, and all the milestones that it looks like we're on track to hit. So yeah, but I should say I'm very glad to hear that you and others in the crypto community are taking this seriously. As I think you should
Well,
be. I
I'm
mean,
also hoping that you're going to be able to help us. But
yeah. Well, yeah. No, look. So some of us are old enough that we remember Y2K, right? Which like could have been a huge deal. Would have been if people hadn't taken it seriously, right?
yeah,
And then the irony is that because people took it seriously and they reacted to it in time, then it just felt to the world like a nothing burger,
yeah.
right? And and the hope is that this will be similar. That by the time we have quantum computers that would threaten, RSA and Diffie-Hellman and so forth, that we all, just would have done the fork by then to, the other crypto systems and other signature schemes that appear to be quantum secure. Now, there does seem to be, an inherent tension here, right? Where like the whole original idea of Bitcoin was that no one is in charge, right? It's it's a full, it's a decentralized protocol, right? It's the code is the law,
It is. It is.
right? As you're right, and so then if you have to make a decision like migrate the underlying encryption from one form to another form, who makes that decision, right? It does seem to be somewhat easier for systems like Ethereum, where at least there is like a committee, there are people who are empowered to make that decision, than it would be for a place where you really need to get
Yeah.
51% of the miners or whatever on board with whatever you're going to do.
Yes.
So yeah, so that is I would say a unique challenge that like a decentralized cryptocurrency faces, right? But there's also all sorts of other there are government agencies, there are companies using just using RSA or using signatures, right? That are already looking into migrating, or in some cases already have migrated
Yes.
to post quantum cryptography.
Yes.
I think that the NIST and the NSA in the U.S. have wanted like every federal agency to be ready to do this by 2031 or so.
Yes.
Which
Yeah. Professor Scott Aaronson of University of Texas at Austin, and the world's leading authority on quantum computer and when is it going to impact us. Thank you very much for coming on this podcast. For those of you, so I'm Eli Ben-Sasson, co-founder and CEO at Starkware, previously co-founded Zcash and co-invented a lot of the ZK, both quantum susceptible and quantum resistance out there in use in blockchain. I'll be having more podcasts on other technological things like what the hell is ZK, what are ZK Starks, what are ZK Snarks, privacy, which is another hot topic, and of course post-quantum security and what it all means to blockchains, Bitcoin and others. So if you want, please follow me on Twitter. You should all go and sign up and read Scott's amazing blog, which is available at scottaaronson.org. .com/blog. Yep. Okay. Thank you very much, Professor Aaronson, for sharing your knowledge with us here today. And let's all avert the quantum flood. Thank you.
Yeah. All right. Well, thanks for having me, and good to see you again.
Thank you.